Hello everyone. For second semester, I am going to take classes on statistical mechanics. Okay, now let us see syllabus of statistical mechanics. It is 5 hours topic, and here we are going to study introduction to statistical mechanics, then statistics of identical particles. Here we are going to study three concepts, that is Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac statistics, and also we are going to derive expression for distribution function in all three cases. Then comparison of Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac statistics. Okay, now let us see some introduction of statistical physics. Up to the end of 17th century, all observed physical phenomena were explained by using laws of classical mechanics or by the laws of electromagnetism. But with the help of these laws, the system which contains many particles cannot be explained due to some mathematical complications. And also these laws, that is laws of classical mechanics and laws of electromagnetism, are failed to explain some of the observed experiments such as black body radiation, photoelectric effect, etc. So to explain these experiments, a new theory is required, and as a result quantum theory came out. When this theory ties its knot with statistics, we get new branch of physics known as a statistical mechanics, which is capable of explaining the physical behavior of all the systems, whether composed of single particle or composed of many particles or large number of particles. Okay, now let us see what is statistical mechanics. That is definition of statistical mechanics. Statistical mechanics is basically aims at explaining the observed physical properties of matter in bulk or macroscopic view on the basis of behavior of its microscopic constituents. Okay, now before going to study Maxwell-Boltzmann, Fermi-Dirac and Bose-Einstein statistics, now let us recall some of the basic concepts. Here we can see that matter, we know that anything which occupies space is known as a matter, and this matter is made up of two or more number of molecules, and these molecules are made up of atoms. And here we can see that atoms are made up of nucleus, and around the nucleus there are different energy levels. In these different energy levels, electrons are occupied. Here we can see that atom consists of a nucleus and electrons. Further, this nucleus consists of neutrons and protons. Protons are having positive charge and neutrons are having, they are electrically neutral. And if you see further, photons are made up of two up quarks and one down quark. The same way, neutron is made up of two down and one up quark. Okay, here we need to remember that the structure of a. Okay, now let us move to the next point, which is very necessary to study Maxwell-Boltzmann, Fermi-Dirac and Bose-Einstein statistics. Consider an isolated system composed of a large number, capital N, of particles, in which each particle is available to its several states with energies E1, E2, E3. At a particular time, the particles are distributed among the different states so that N1 particle can have energy E1, N2 particle can have energy E2, and so on. The total number of particles is given by capital N is equals to small n1 plus n2 plus n3, or we can write it as a sum of ni. And the next point is, we assume that total number of particles remains constant for all process occurring in the system. So the total energy of the system is E is equals to N1 E1 plus N2 E2 plus N3 E3 so on, which is equals to summation Ni Ei. Okay, let us try to explain this point by taking an isolated system as an example. Here I am going to consider an isolated system. It is an isolated system and it is having n number of atoms or particles. It is having n number of particles. Isolated system means this system is not going to exchange anything, that is, it does not going to exchange number of particles and it does not going to exchange energy to the atmosphere. Okay, now if you consider a single atom in the system, then this atom is made up of nucleus at the center, and above nucleus or surrounding nucleus there are different energy levels are present. Let us suppose the energy level which is near to the nucleus is E1 and next to it is E2 and the next level is E3 and so on up to Ei. Ei be the ith energy level. And also we know that electrons are going to revolve around the nucleus and these electrons are going to occupy energy levels, depends on its energy. Some electrons may occupy first energy level E1 and some of electrons may occupy second energy level, depends on its energy. These electrons are going to occupy different energy levels. And also let us suppose if electrons have energy E1, then we are going to denote, and in general we are going to take electron as a particle. Let us suppose a particles having energy E1, then we are going to denote it by N1, and if particles are having energy E2, then we are going to denote these particles by N2, and the particles those having energy E3 are, we are going to denote this by N3, and the particles which are having energy Ei, we denote these particles by Ni. Okay, now let us come to this system. This system is having n number of atoms or n number of particles, but all these particles they do not have same energy. That is, some of the particles they have energy E1, and some of the particles they have energy E2, and some of the particles may have energy E3, and so on. So here we are going to write two equations. The first one is N, that is the total number of particles present, which is equals to the N1. N1 is the number of particles those present in the energy E1. It belongs to the all the atoms, those particles having energy E1, and plus N2. N2 be the number of particles those have energy E2, and N3 be the number of particles those have energy E3, and so on up to Ni. Or we can write total number of particles summation of I into Ni, sum of particles. This is the total number of particles, and here we need to write one more equation, that is total energy of the isolated system, that is capital E is equals to, which is equals to N1 E1. N1 be the number of particles which are present in the energy E1, and N2 E2 be the number of particles those have energy E2 in the isolated system, and so on up to Ni Ei. And we can write this equation by E is equals to summation I Ni Ei. These are the two equations. This is the total number of the particle, and this is the total energy of the isolated system. Total energy of the isolated system is equals to N1 E1 plus N2 E2 plus so on Ni Ei. Okay, now let us study different types of system. Here we are going to study the first one is microcanonical system. Here we are going to consider a system which is having n number of particles, and outside this system we observe that there is an insulation, so that there is no exchange of particles and energy to the atmosphere. Microcanonical system is very simple. There is no exchange of energy and particle, and we can also call microcanonical system as an isolated system. And the next system is canonical system. We can also call canonical system as a closed system. Here also same, we are going to consider one system, and there are n number of particles in this system, and E be the energy of the system. And here in closed system we can observe that there is only exchange of energy to the atmosphere, and there is no exchange of particle to the atmosphere. And the last one is grand canonical system or open system. Here we observe that here we are going to consider a system which is having n number of particles, and E be the energy of the system. In this system both energy and number of particles may exchange to the atmosphere. We call this system as an open system. Okay, thank you.